This session entails the discussion of boiling point, the vapor pressure, and how intermolecular forces affect the boiling point and vapor pressure of the molecules. So before we jump into the examples, let me briefly explain what boiling point and vapor pressures are. In simple terms, you can say the boiling point is going to be the temperature when liquid starts to boil, but when you take a chemistry or physics course, you have to be a little bit careful with the definition. And the boiling point is going to be the temperature when the vapor pressure is going to be equal to the external pressure, which is whatever you have in the atmosphere. And similarly, you can define the normal boiling point if your external pressure is exactly 1 atmosphere, because that's what the normal pressure is supposed to be in the atmosphere, and that's what you have on the sea level. And obviously, when you go on a higher altitude, your pressure decreases, or if you go below sea level, it's not 1 atmosphere anymore, and that's when you just have a boiling point. But when it's 1 atmosphere, you will have it normal boiling point. And that's one of the reasons the water would boil at maybe slightly higher or less than 100 degrees Celsius temperature because it depends on the pressure of the surroundings. Okay, so let's talk about what a vapor pressure is. So suppose I have this flask here, and it got the cap on the top of it, and I got some water in this. So initially, what's going to happen, the water that's going to be on the top of the surface of this liquid, the water molecules, they're going to start escaping into the vapor phase. So I can kind of draw some of those into the directional here. So I'll have some H2O just starts kind of moving onto the vapor phase. And then as the time passes by, you will have more gas molecules being made here. And then there is a good chance that you will have some of those coming back into the liquid phase, because it's going to set up in a dynamic equilibrium. So to set that up, it may have some of those coming back into the liquid phase. Obviously, if this was not capped, you would lose those water molecules once they form the vapors. But in this case, they will just stay in that perimeter, and once they start setting up the equilibrium, they will be coming back to the liquid phase. So eventually, what's going to happen, you will have this rate of evaporation and this rate of condensation equaling one another. So what that really means, the amount of water molecules evaporating and the amount of water molecules condensing are going to be the same. So I can draw 3 arrows kind of going up, and then I can probably draw 3 arrows kind of going back down, which tells you the rate of evaporation is going to be the same as the rate of condensation there. Okay, so once you reach this so-called dynamic equilibrium, the pressure that's going to be exerted by these gases or these vapors onto the liquid surface and vice versa is going to be called the vapor pressure. Now, how fast and how quickly these water molecules in this example will go onto the vapor phase is really dependent on how strongly these are held with one another. So when I look at the water molecule, recall water molecule make hydrogen bonds, and hydrogen bonds are actually very strong. So the hydrogen bonds are going to be made between the partial negative charge of one of the oxygens of one molecule with the partial positive charge of the hydrogen of your second water molecule. So in this case, both the hydrogen bond donor and the hydrogen bond acceptor is actually in the same molecule. And now you have two separate molecules being condensed together. So you have to actually break this intermolecular forces in order for water to leave in the vapor phase. And if this intermolecular force is stronger, it's going to be harder to break it. And as a result, you will have a low vapor pressure. So anytime you have so-called strong intermolecular forces, you will run into into a position where it's going to be low vapor pressure. So in order to make the vapor pressure equal to the atmospheric pressure, which means reaching the boiling point, you would have to heat it up at a high temperature. So the boiling point is going to be high. All right, and if you have low vapor pressure, high boiling point, you call those liquids to be non-volatile. And obviously water is one of the examples, and I can talk about glycol is another example, because they all make very strong intermolecular forces and they resist into changing into the gas phase. Similarly, if you have weak intermolecular forces, you will have high vapor pressure. And one example I can literally take is going to be C8H18. That's your octane molecule. And when you spill a little bit of gasoline when you're filling up your car gas tank, the gasoline quickly evaporate. That's because it makes weak intermolecular forces, which are going to be the dispersion forces. And since it makes weak intermolecular forces, it's going to have high vapor pressure and it's going to have low boiling point. And as a result, you're going to call that a volatile. All right, so it's important to know the relation between these intermolecular forces and how your boiling point and vapor pressure is going to behave based on that. Okay, so now let's take a few examples here and see what criteria you're going to be looking for when you arrange those things in terms of boiling points and vapor pressure. So suppose I have this case 1 here. The case 1 is usually looked at when you have molecules with similar molar mass. They don't necessarily have to be exact same molar mass, but similar molar mass and maybe roughly the same size, not a big difference in terms of the size. In those cases, the type of intermolecular forces that you're going to make will matter. Okay, so you're going to be looking at what intermolecular forces each molecule is going to make. So suppose I call this molecule A, this is B, and this is C. Now, this if it becomes difficult, you may want to draw the loose dot structures of those. And just because you see an oxygen and hydrogen in there, that doesn't necessarily mean they're going to be chemically bonded with one another. So when you actually draw out the intermolecular, draw out this structure, you will see how each carbon has 3 hydrogens and oxygen is like the center point there. So you don't really have any hydrogen connected to the oxygen here. So when you look at the second one, we have 3 carbons in the chain. And the first and the third carbon getting 3 hydrogens each, and the second carbon getting the 2 hydrogen. And when you look at the third one, the first 2 carbons, first carbon getting 3, the second carbon getting 2 hydrogens, and then you have an OH. Now in this particular case, you do have actually an oxygen directly bonded with your hydrogen. So remember, when you're trying to figure out the different types of intermolecular forces, always look for the hydrogen bond, because those are usually the easiest to recognize. You must have an oxygen or an oxygen or a nitrogen or a fluorine directly bonded with the hydrogen. And if that's the case, you would be able to make a hydrogen bond. So this is capable of making hydrogen bonds. When you look at the first one is actually capable of making only dipole-dipole, because this is going to be polar because of the presence of the oxygen there. And if I want to draw the dipole moment there, I can clearly say, okay, this oxygen is going to be partially negative, and both of those carbons going to be partially positive. So you're going to have a net dipole going, you'll have dipoles going into the oxygen. So they're not really canceling one another out because it's a bent molecule. If you still have issues with drawing these loose dot structures, you may want to watch the other video that I have posted just on loose dot structures. Okay, so then the second one here, all you really have is a carbon-carbon bond or a carbon-hydrogen bond, and all those bonds are nonpolar. And since those bonds are nonpolar, this overall molecule is going to be nonpolar, and that's going to be giving you only dispersion forces. Okay, now I do want to mention here, a lot of times you will have molecules making dispersion forces all the time. Like for example, this first one, in addition to making dipole-dipole, it's also making dispersion forces. Okay, and the same story with this third one, in addition to making the hydrogen bond, that's with the second part of the molecule, but this first part of the molecule is going to be making dispersion forces as well. But when you're looking at the molecules with similar molar mass and similar size, you mainly focused on the strongest intermolecular force a particular molecule is going to make. So obviously in case of C, you'll have hydrogen bond, so that's going to be the strongest. A is going to be the second strongest, and B is going to be the weakest in this particular case. So let me just scroll this down. So then I can clearly say, in terms of the boiling point, and we are arranging those in increasing order. So B, since it's making only the dispersion forces, so those are going to be the weakest, and the hydrogen bond is going to be the strongest here. Clearly say B is going to have the lowest boiling point, followed by A, which is going to have a higher boiling point than B, and then since C making the hydrogen bond is going to have the highest boiling point. And when you look at the vapor pressures, it's just going to be reversed. All right, so whoever has the lowest boiling point will have the highest vapor pressure. So, and whoever has the highest boiling point, or whoever makes the strongest intermolecular forces, will have lowest vapor pressure. So C is going to have the lowest vapor pressure, followed by A, and then B is going to have the highest vapor pressure. So that's how you're going to be looking at it. Okay, so then let's take another example where you have a different molar masses. Okay, so if you have a different molar mass, and if they make same type of intermolecular forces, then whoever has the bigger molar mass, or whoever is bigger in size, technically wins over in terms of the boiling point. That's because in every single case here, let's call this A, call this B, call this C, they're all actually going to be making dispersion forces, because all you really have is a carbon-carbon bond or a carbon-hydrogen bond. And both of those bonds are nonpolar, and if you have only nonpolar bonds, it's just going to be dispersion forces. And since they are making only dispersion forces, this C, since it's the biggest molecule and also it's going to be the highest molar mass, it's going to be making the most amount of dispersion forces. So you'll have most dispersion forces being made here. And since C3H8 is the smallest here, is going to be making the least dispersion forces. So more you have, the better you are in terms of keeping molecules together. And if I look at these molecules in real life, C3H8 is actually propane, and propane is a gas at room temp. Okay, C8H18 is an octane, which is the active ingredient in gasoline, and it's a liquid at room temperature. And then when you look at C20H42, those are going to be your waxes. So remember, the waxes are actually solid at room temperature. So you can clearly see how, even though you have the same type of forces being made, the size increases the boiling point in this particular case. So when I put them in the order of boiling point, A being the least number of dispersion forces being made here, is going to have the lowest boiling point, and that's why it's a gas at room temperature. And then B, it's a liquid at room temperature, but it literally have a low boiling point. As soon as you spill a little bit of gasoline, you can see it evaporating very quickly. So B is going to have relatively higher boiling point than A, and then C, since it's a solid at room temperature, you must have to heat it up in order to boil it out. So it's going to have the highest boiling point in this particular case. When I'm arranging those in terms of vapor pressure, is obviously just going to be opposite. So C is going to have the lowest vapor pressure, followed by B, and since A has the lowest boiling point, the weakest intermolecular forces in this case, or weakest amount of intermolecular forces, it's going to be having a highest vapor pressure. Okay, what about if you have a case where you have the same molar mass but a different surface area? And I can take an example of maybe C4H10, which means in one case I can place those 4 carbons in a regular chain, something like that, and then the terminal carbons will have 3 hydrogens, and the middle carbons will have 2 hydrogens each. That's one way of writing this formula. The other way, or another structural formula for this C4H10 gonna be, if you have only 3 carbon in the main chain, and then one of the carbons is going to be coming out from the second carbon. So it's like you have the same formula for both of those, but they are different structures, so they're going to be called constitutional isomers. So in case of one, in the first case, you have a bigger surface area, and in case of two, you have a smaller surface area. So anytime you're looking at molecules that has the same molar mass and they're making the same type of interactions, because both of them will be making dispersion forces, because all you really get is carbon-carbon or carbon-hydrogen bond. And in those cases, you look for the surface area, and whoever has a bigger surface area kind of wins in terms of the boiling point. So the first one, let's call this A and call this B. When you arrange those in terms of boiling point, this A is going to have a higher boiling point B just because it's got a bigger surface area. And when you arrange this in terms of vapor pressure, B is going to have higher vapor pressure than A just because it follows the opposite order than the boiling point. Okay, so those are the 3 criteria you're always going to be looking into when you're trying to determine the order of boiling points and the vapor pressures in different molecules. Alright, if you have any questions on any of this boiling point and vapor pressure scenarios, feel free to leave any comments in the section below.